Good afternoon, everyone. My name is Lily Zhao, a Flatiron Research Fellow with the Center for Computational Astrophysics in New York City, and I'm here to talk about the EXPRES Stellar Signals Project, or the ESSP, which is a community-driven effort from disentangling center of mass velocities, for example, from a planet orbiting and pulling on a host star, and photospheric velocities, which may arise from stellar signals such as intrinsic variability or activity features. This stellar variability can give rise to a range of different features, for example, oscillations, which are shown here, where the star itself will be moving in and out, which happens on the time scale of minutes and will contribute an RV scatter of 0.1 to 1 meters per second for sun-like stars. There's also granulation and supergranulation, these coherent patterns, which change on the time scale of minutes to hours and can contribute an amplitude from anywhere from 0.4 to 0.8 meters per second. And of course, we have pesky activity features, which include darker areas such as spots and brighter faculae and plages that persist on the timescale of months to even decades, and will introduce a signal on a timescale of the stellar rotation rate as these features rotate in and out of view. And depending on the size of these features, the size of the star, and also the rotation rate, these can introduce an RV scatter of up to 10 meters per second. And since this persists currently in the EPRV field as one of the largest sources of error, I started the EXPRES Stellar Signals Project, which got together teams from over all of these different institutions containing over 50 researchers that together tested over 21 different methods on the same provided EXPRES data. So each team was given these same data sets to try their different methods on. And because this produced a self-consistent assessment of what these different methods were doing, we were able to establish the state of the field, understand what people were trying, and kind of use that to establish some future recommendations for the field. The data made use of EXPRES data, which is installed at the Lowell Discovery Telescope near Flagstaff, Arizona, which is where you might fly in if you were interested in seeing the south rim of the Grand Canyon. There's a 4.3 meter diameter mirror on the Lowell Discovery Telescope. And this telescope is really slick because it has this instrument cube that allows us to switch between the different instruments with just a click of a button. And what this practically means is that this telescope is able to schedule a lot of partial nights. And so instead of having the entire night devoted to one instrument, you'll get instead a half night or even a quarter night. And so in delivering the instrument, the EXPRES team was promised up to 70 nights per year. And if we broke that down into quarter nights, we could be on sky for conceivably up to 280 partial nights per year. Additionally, in October 2020, we installed a solar telescope, as shown here on the little green shed behind the telescope, that's been operational since then using EXPRES. And so here I show EXPRES, or the extreme precision spectrograph, with the optical bench and its optical path overlaid with some of the pertinent optical elements labeled and pictured. EXPRES is an optical spectrograph, and so its wavelength range goes from 390 to 780 nanometers. It is both vibrationally stabilized with many different areas housed in a vacuum chamber, and so the pressure is also kept constant, and passively thermal controlled. And along with other stuff that makes it one of those so-called next generation spectrographs with a pretty high resolution of 120 to 150,000 with a median resolution of about 137,000. In terms of stability, now that we've been on sky for almost 3 years, we see that for the quietest stars on sky, EXPRES is regularly returning sub-meter per second precision. And so here I show 6 of our quieter stars and the associated RMS with them. And so nothing has been done to these RVs except our typical pipeline, which uses a forward modeling chunk by chunk technique. And you can see that the scatter over the many years that we've been observing these stars with these ranges from 60 to 80 centimeters per second, with an intranight scatter of 20 to 30 centimeters per second, which is what you'd expect from the analytical errors given by our pipeline. And so another way to think of this is, since these are the quietest stars that we're looking at, if we were to look at a noisier star, so a data set where some stellar signals were present, and there was a method successfully cleaning out all contributions from the star from this data set, then this is the level of scatter you'd expect to reach by successfully separating out the stellar component from the component of the star that we're actually measuring. In other words, this is the minimum RMS you can expect just due to instrument noise alone with no additional added stellar signals. So for the EXPRES Stellar Signals Project, or the ESSP, we got a range of different methods that seem to be acting along 3 main philosophies, which I've separated here into the different columns. And so for the different methods, they either came up with some sort of metric, so some sort of measurement of how much activity that was present in the observation at the time we took it, something like an activity indicator, so something to tell us the magnitude of stellar signals we expected to see in each observation. The other type was the mitigation category of methods. And so these methods came up with a different way in which to take information like the metrics that people came up with or classic activity indicators and understand how to map that measurement of activity level to an RV correction. And so many different mitigation methods were trying to explore how exactly to link metric of activity indicator to the exact effect we would expect it to have on RVs. And lastly, the third main philosophy is this idea of separation. And so many teams took what we knew or expected we know about stellar signals and the different ways that they'll affect the RVs or the spectra that we see, and separate out the effects that we can say are purely come from stellar signals versus from center of mass changes. And by separating those out, you could isolate which of the proposed measured RV were due to stellar signals versus a true center of mass shift. And so, for example, we expect activity to present itself as an asymmetric signal. And so there's a lot of work focused on separating out asymmetries from bulk center of mass shifts, or sorry, bulk center shifts of the lines. Or we'd expect stellar signals to vary on a different time scale than we expect a planet to orbit. And so the increased variability of certain signals versus stability that we'd expect from a very consistent over a longer period of planet orbiting was used to separate out different effects. The methods here are also ordered by the amount of data that each method took in, which differed between indicators. So just the activity indicators, the classic indicators that were given, which each team was asked to use, the ones that were provided, and the RVs that, again, were provided and consistent across all the different methods used. Other teams use the CCF or the cross correlation function, which can be thought of as a way of deriving RVs that also gauges the average line shape of all the lines in the spectra. Others use the spectral information by isolating specific spectral lines that they thought would be better suited for finding clean RVs. And these are a class of line by line methods. And lastly, other methods use the complete spectral information that were provided. So going from the 2D data and using the spectra pixel by pixel to understand what effects could be coming from stellar signals versus orbiting planets. So like I was saying, I wanted to go through the methods by increasing indicators. This is also how the methods are ordered in the paper discussion. And so, of course, classically, we have decorrelation, where you take your activity indicator, you take your RVs, you plot them against each other, you fit a line, and you subtract the correction out that you'd expect from your RVs. And so many groups since then have been working on more advanced statistical models besides fitting a line for figuring out what the indicators are telling us about the RVs, including using Gaussian processes as a more flexible way of gathering that information, or going into the Fourier domain to make sure that the phase dependencies don't have much of an effect on the correction that you're solving for. Other methods chose to concentrate on the cross-correlation function as a sort of representation of the average line shape change that you see in your different observations. And so the CCF has the benefit of averaging the signal of the line shape changes across all the different spectral lines, which in an EPRV, even high resolution spectrograph like EXPRES, you might get 4 or 5 pixels per line. And so in one way, you're building the signal by averaging them all into this one CCF. But in another real way, you're averaging away a lot of the information that you might get from specific lines that change one specific way, but the majority of the lines do not. And so other methods take advantage of that fact by considering each spectral line individually and trying to figure out whether some lines contain more RV information or other lines contain more stellar signal information, and how to combine those two types of lines into cleaner RVs. And lastly, we have a growing amount of methods that are using the full spectral information, so the entire wavelength versus intensity information, to figure out how each pixel is changing with regards to different amounts of stellar signals that is captured by each observation. And so each of these different methods, though they operate around those 3 different types of philosophies I discussed before and are using different types of information, they all share a set of common assumptions that we should keep in mind as we talk about how these different methods work and things that are worthwhile to do in the future. So for example, regardless of what sort of method you are using or what sort of information, a lot in some way are indicator dependent. So those that use indicators, of course, but others are informed by how lines vary according to indicators, for example, or how the pixels may vary according to some sort of indicator. And so, of course, they'll be sensitive to anything that is being captured by your indicator. But if there's any type of stellar signal that persists and remains unmarked by changes in the indicator value you're using, then this method will not be able to catch that degree of stellar signal variation. In fact, all of these methods also assume a linear correlation with the indicators in question, except for the Fourier-Domain PCA option, which uses the Fourier-Domain to get rid of the phase dependence. Many of the methods also make use of a Gaussian process model, which of course invokes explicit assumptions based off of what kernel you should use, the sort of hyperparameters that are relevant for your different issues, and the best way of deriving both the appropriate kernel and the appropriate hyperparameters for that model. Another set of methods made use of principal component analysis. And so this involves assumptions of what your primary variation is within the spectra and attributing that either to stellar signals or whatever you're trying to disentangle. And with most PCA methods, especially ones that try to use it as a denoising method, it also invokes a sort of assumption of the dimensionality of your issue. So how many principal components can you use before you're adding in noise? Beyond just using PCA as finding new basis vectors, a lot of methods use other sort of basis vectors with different benefits, such as being invariant to shape shifts or having something that separates shape changes versus shift changes. And so with all of these different methods, they are also making some sort of assumption or some sort of decision of what sort of basis vector is appropriate for capturing the different signals that you are either interested in throwing away or interested in investigating further. Other methods make this assumption that any increase in scatter is implicitly tied to activity. And so they used things that had larger scatter or introduced larger scatter in the final RVs as a way of tuning parameters or something like that to decide how well their method was doing. And lastly, there's a very strong assumption in the field that anything that causes an asymmetry in your lines is tied to activity. And in many cases, the reverse is true as well, that all activity does is give rise to asymmetric things. And so if you get rid of the asymmetric aspect of the different signal, then you're clear to go for the shift-driven changes afterwards. And so the first point I'd like to emphasize as a result of this study is that we should really be working on our understanding of stellar signals. Stellar signals are identified through these different things, indicators, asymmetry, or increase in scatter. But we should take a step back and see if we truly understand the scope of necessary activity metrics. Do we have activity indicators that are capturing everything? Do we have simulations that perhaps will show all the different effects of stellar signals? And we can use that to figure out if the models and the data that we're giving these models is capturing all the signals that we truly need to disentangle. And so I'll move now to talking about some of the method results, but first I wanted to highlight the exact nature of the EXPRES data that we gave out. So the EXPRES data, which we gave out starting from the spectra all the way up through CCFs, indicators, and RVs. So each team was asked to use the same data that we provided to keep things consistent. And we did it for these 4 different targets, which I've ordered here from kind of most active to least active. But a lot of these data sets have very interesting properties that we thought would help us cast some light on how the different methods were doing. So for example, we have most active over here, HD 101-501. It has an RMS initially of about 5 meters per second, but despite it being very active and therefore having the largest activity signal, it did have the least amount of data points. So there were maybe only 44, I think, data points here, whereas the other data sets numbered more around the 150 to 180 data points. We also gave out HD 26965, which is a really interesting case because in the literature, there's been published both a rotation period detection and a period detection with very similar periods. And so this is a very interesting case where we have the stellar activity and the planet signal right next to each other. And so it'd be really interesting to see with this new EPRV data set and all these different methods trying to disentangle those 2 effects, what kind of results we would get. The next one we gave, which is slightly less active with an RMS now of around 2 meters per second, is Tau Ceti. And Tau Ceti, because it's such a bright star, is something we were able to hit with a very high cadence. And so while most of these stars, we did 2 to 3 consecutive observations per night across these different observing seasons. For Tau Ceti, there were 2 nights where we tried to get 30 minutes of consecutive observations. And so within this data set, there's 2 nights where there's 20 consecutive observations within the same night. And on one of them, we see pretty clear evidence of the oscillation pattern. And so here we give a data set of very high SNR, but also this very high cadence that's capturing a different time scale of activity. And lastly, we gave HT34411, which has the lowest initial RMS and the seems to be the least active of all the 4 stars. So we have a range of activity types, whether there's a planet or not, and also the range of the different time samplings to kind of see how these different methods do. And so maybe it's not too shocking that the method results vary depending on which data set that they were tested on. And so as an initial look at the results, I have these bar graphs here where the methods for each of the target data sets is ordered by decreasing RMS. So as you go left to right, the RMS will always be lower, but the specific method order will change from data set to data set depending on the RVs that the method returned for that particular data set. Within each graph, we have a black bar and a horizontal line showing the original RMS of the given EXPRES RVs, where nothing was done to mitigate anything with stellar signals except our typical RV pipeline. And the different bars are colored by the amount of data that they use. And so we tried, for example, the classic linear decorrelation with indicators, which is shown in brown. And you can see here that they're all clustered pretty close to the black bar, meaning they did very little to reduce the scatter and the resulting RVs, showing that in this regime of EPRVs, we really need to move beyond this method that has held so true for so long. But other than that, you can see that there's a huge range of how the methods did. It would vary from star to star. And so there's really no consistent performance. We couldn't look at this and be like, okay, this method gets first place, they're the best, they win, let's all talk, because if that were true, I think they would be giving this talk right now. And so, I also wanted to highlight that at the same time, if you look at the bar heights, you'll notice that the sub-meter per second precision that we're trying to go for in order to, for example, achieve the stability that we've seen with EXPRES for some of our lowest or for our quietest stars, is just not being achieved regularly by any of the methods. Which now brings me to my second point, innovation. None of the methods are really consistently and across all these different stars, reducing the RV scatter to the needed sub-meter per second levels that we all want to be detecting the smaller, more Earth-like planets that we're after with this EPRV work. And so we should probably consider what our methods are missing and consider innovating on the different methods. And perhaps a good first step is to compare, contrast, and combine the different methods we already have. Take all the methods that make some sort of metric and combine it with the different methods that use that metric in a different mitigation sense. Look at all of the methods that separate out the shape and shift driven elements, for example, and see if they're looking at the same thing. And so there's a lot of things we can do right now to kind of understand the field, the kind of field of play a little bit more. And then by doing so, we may be able to find more holes in our understanding or holes in how our methods are being implemented to try and reach this sub-meter per second level that we're after. Another thing I want to highlight with these bar graphs is that you'll notice that in each of the bar graphs highlighted now by this green area, there's these kind of plateaus of the bars. So a bunch of these methods are reaching pretty similar RMS values. And so we decided to take a closer look at that, because while using real data has a lot of benefits, for example, you know that what it's capturing is real stellar noise, the cadence, all of that is realistic because it is real data. But we don't have the true answer at the back of the book of what the stellar signals are. But because all the methods are using the same data, we know that they're tracing the same stellar signals because the same stellar signals is being represented in the data that each group is using. And so for these methods that are returning a similar RVRMS, we'd be expected them to be tracing the same signal because the same signal is present in all of the data. And so to kind of get at this, what we did instead is we took all of the methods and did a simple Pearson correlation comparison with all of the other methods against the activity RVs or the RVs that they removed from the RV time series. And so here along the Y and X axis, we have the methods ordered the same way as they were in the previous plot. So by decreasing RMS, where the bars are kind of recreated on top just to give you a sense of scale. And at the intersection of any two methods, the marker is colored based off of the Pearson correlation coefficient. So how linearly related the two activity RVs returned by the methods are. And if this correlation coefficient is greater than 0.4, which is a significance metric we decided based off of the error properties of the different data sets, then it's shown as a square. So for example, for the most active case, HD 101.511 up here, you can see that most of the activity RVs are correlated, but this was a data set in which the activity signal dominated. In a lot of the other cases, we see this real lack of agreement between the different methods, despite them all being on the same data. And in some cases, even methods that return the same RV-RMS don't agree with each other. And so it becomes really unclear what signal these methods are exactly subtracting out, even to get similar RV-RMSs. It's a great demonstration of the fact that RMS or scatter is really not a great marker of what your method is doing, because even if it's reducing the RMS to some degree, it could be removing any signal, stellar or otherwise. Furthermore, if we look at the 26965 data, which had that stellar rotation period of the planet signal very close to each other, I have now shown, I'm showing here the periodograms of the clean RVs in C and the activity RVs. So what RVs signal people attributed to shift-driven RVs and which people attributed to the stellar activity. And you can see that in the different methods, any method that thought the signal in the period range of interest, where the planet period and the stellar rotation period falls, is highlighted in a blue axis. And any method that said that that periodicity was attributed to the activity signal, so it's more prominent in the activity RVs, is highlighted in orange. And so despite using the same exact data, the different methods couldn't even agree on whether there was a planet around this star or whether it was all stellar activity. And so we have this kind of confusing understanding of what the methods are doing exactly. And we've really just used some pretty basic tests here, the RMS, the correlation, and this periodogram analysis. And so the third thing we should really focus on is the interpretability. We know we have this lack of agreement between methods. And so we need to better understand what exactly these different methods are doing. And two, we need better metrics for the method performance. And so we should be, instead of just using RMS, we should have some other test that truly gets at the question of either, is this getting rid of stellar signals, or will it preserve planet signals, for example, and what exactly it's removing? And part of the interpretability will be using tests with well-understood data sets. So for example, archival data sets of really well-understood systems, or the solar data set of arguably the best understood system with injected planet signals, and we can see how well that's doing. And so along that vein, I'm now working with primarily Annalise, Xavier, Eric, and Zhao on combining solar data sets from the two HARPS instruments, EXPRES and NUID. And so this will be a really exciting data set because, as you can see here, pictured just on a random day that I chose, I have the different data sets from all these different solar telescopes. We have a bunch of overlap for all of them. And we have this much longer time baseline because of the different areas in the world these spectrographs are. And so by combining this data set, we can disentangle any instrumental noise using the overlap regions. And we can inject Keplerian signals and have this great data set for testing these methods on a system we know that captures real stellar activity and uses all of this great data from all of these spectrographs. And so I'll put up my summary slide here. I've crossed out EXPRES because it is no longer just us. It's been really encouraging to see how the community come together, both with regards to how willing they are to share data and their method and the work that they put into this. So though I'm the one who's talking to and all of you are muted, this really was a community effort. And I've been really privileged to have all these people helping out with this project. And so I'll leave up these 3 points and I'll take questions now, maybe. And then after we do questions, we can move on to the discussion aspect of future things we might want to pursue.
That sounds like an excellent plan. And thank you so much, Lily, for that overview of how the project is evolving. I welcome folks to do the little clapping hands emoji while we're all still muted. And then please raise your hand, put questions in the chat. Or if your hand is raised, I'll call on you and then you can unmute yourself and ask your question to Lily. So I see one hand up already. Ray Holcomb, go ahead and unmute and ask your question.
Hi, first of all, thank you so much. This was a fascinating talk. I was really intrigued by your kind of assessment that the RV-RMS is a little coarse for trying to evaluate the total amount of activity in a system because it does fold all these metrics into one. I was wondering, could there be some utility in, rather than just doing total RV-RMS, maybe defining RMS on different timescales and using that as maybe because you'd expect the different stellar signals to inject, variability on different timescales. So could that be a way that we could potentially probe different sources of variability in the light curve rather than just trying to fold it all into a single metric?
Yeah, that's a really interesting idea. Emphasizing the different timescales of the different stellar signals, I think indeed will be key. And one of the things that we have looked at, for example, this is not exactly what you're talking about, but we didn't only look at the overall scatter, but we also looked at the internight scatter. So how much scatter between the different consecutive observations between a night. And so there you would assume that if that got lower, because the stellar activity probably isn't changing that much over the time scale that we're observing, then you are removing some sort of scatter. But I think one of the larger issues of just looking at scatter is that the different methods worked so differently. It wasn't quite a fair comparison for all of the methods. So for example, some methods focused, for example, if a method just used PCA, it would be sensitive to any sort of variation that you're seeing in your spectra, whether it be from the star, from the atmosphere, or from your instrument. Whereas some other methods focused on this like shift shape change. And that's very much more focused on what we think we understand about stellar activity or something like that. And so I think there's definitely some ways that RMS could be made more useful. And I think you're right with that. But I think ultimately it's not going to be our like final answer, if that makes sense.
Thanks so much.
Okay, Sam, I see your hand up. Go ahead.
Hi, Lily. Thanks for a great talk. I have a only peripherally related question, but it sort of pertains to your last slide, which is there have been a handful of like Earth-facing CMEs and other interesting transient events on the sun in the past like year, I think. And we've done a course check. Some days we have new data, some days we don't. But are there any plans to go into these, admittedly, sort of transient events, but ones that are potentially astrophysically quite interesting and doing a cross comparison of those specific days?
There's no plans currently, but I think that would be a great use of this new collaboration. The thing we're focusing on right now is making sure that our different pipelines are creating RVs that are comparable. So for example, if these different instruments have different wavelengths, we tried the RVs that I've showed in the previous slide, try to make use of the same CCF mass, but because of the different wavelength ranges, the slightly different order boundaries, some of the lines weren't included. And so I think a lot of the work we're doing here, though I'm talking about it in a Stellar Signals project, will be really beneficial for being able to compare our views across these different instruments in general, and how to make sure that their differences aren't coming from the way that you're deriving your RVs and the way that you're extracting the spectra, et cetera. And so once that's determined through this effort, it'll be a lot easier to do things like the ones that you're suggesting, Sam.
Okay, other questions for Lily? I'm going to ask one, but in the meantime, folks, feel free to raise your hands or put questions in the Zoom chat. So Lily, as you start doing this broader collaboration with the two HARPS facilities and NUID, do you have a sense of how many days provide a useful amount of overlap? Because I imagine there are different weather patterns on top of these different areas, or there are things like the monsoon shutdown that affects Arizona. So on average, what kind of combined coverage do we get? And is there still utility in days where you only have coverage from a couple of the facilities, or are you restricting to days when you have coverage from all four?
Yeah, so that's a great question. The thing we're doing right now is we're focusing on a month of data because a lot of this data is still proprietary, and so we don't want to give out everything with the first go. And so this month of data was decided, it's somewhere in May 2021 as the time where we had the most overlap, and all of the instruments had the greatest number of high quality observations. So I believe we looked at a full year of data, and there was a lot of good options, but as you mentioned, the monsoon and the Canary in Arizona will hit differently than when the Canary Islands have a shutdown. And so that's some limitation. But because we have this area of overlap, I think that's enough to understand how the different instruments are varying and get a good grasp of how to combine them, which will carry over to when they're not overlapping. But most days, there's this very clear overlap between all the instruments, and it looks great. I wish this was just like a random day I picked. And so this is, I think, pretty representative of what most days look like. And of course, EXPRES and NUID have the benefit of being like a 2-hour drive from each other, or 4 hours.
Something to be said for being, next to each other and looking at the sun. Okay, other questions from the audience? If not, we can move over to the kind of discussion portion of this, but last chance to raise your hands or to pop things in the Zoom chat. Okay, it looks like you've, oh, no, there's a hand. I gotta find it. Jalen.
Hi, Lily. Thanks for the great talk. So my question is actually related to the discussion that we might follow later on. So in order to look at whether the different methods are overfitting the planetary signals, previously we discussed this because if you were trying to inject a planet into the spectrum, it might be difficult, but it's easier to inject a planet into the CCF. At least on the CCF, you can just shift the CCF by some specific amount by some interpolation. So I wonder if it's worth like starting injecting planets in the CCF. So for those methods that only uses the CCF, we can start such a comparison. And so when we are ready to inject the planetary signals in the spectra, then at least we can gain some experience on this kind of comparisons. So I wonder if it's worth establishing such a subgroup. So in one slide, you show that there are different methods, one that uses CCF and one uses line and one uses the spectra. So it might be worth to establish a subgroup of those methods that uses the CCF and do this comparison and planetary injection.
Yeah, I really like that idea. We did explore briefly doing injection recovery tests for this ESSP paper, the second one in the series, but we decided it was like too much for the paper that is already way too long. And so we did some work injecting it into the spectra, and we're, I think, 90% of the way there. And Michael Quitnier was so helpful with that process, and it was mostly figuring out different telluric models. And I think the original idea was injecting it at the spectral level and then using that spectra to derive the CCFs and all the way down. And that way, all of the methods would be using the same data. But I definitely see some utility in doing that. But for example, as you said, also injecting it perhaps in the CCFs or in the RVs themselves. And if the methods that use that data get different results for the CCFs, for example, where we just injected the RV in the CCF versus the CCFs derived from the spectra in which we injected the planets, then that would be a great indication that the way in which we're injecting the signals at the spectral level is doing something wrong. So I think that's a really valuable test.
Mm-hmm.
Okay, and David Ciardi, I see your hand up, so go ahead.
Hey, Lily, thanks for that really nice talk. Was there any evidence or was there any exploration of the different techniques and their sensitivity to the number of data points available or the organization of the data points? That is, some methods just did better with more scattered data versus more highly sampled data, that kind of idea.
Yeah, so there's a lot of things we tried to explore with the method results. And so if you look at the paper, there's a method that lists all the different methods that were tried. And along that, there's like a list of, for example, whether they have any requirements for how much data, the time sampling of the data, and also like the amount of time it takes for the method to run. So whether you can do it on a laptop or you need a supercomputing or something like that. And so it's something that I made some plots at some point where I grouped all those together and saw if there was any patterns. But unfortunately, I was still using just the RMS at that point, which harkens back to the call for better metrics. And the difference in how the RMS theory, the relative RMS each method returned for the different targets was so scattered, it was really hard to get a clear picture for that. But I think it's a really important thing to keep in mind because it's something that should set different methods apart, you would think conceptually. And so it might be a good thing of seeing if that pattern does come out clear, maybe it's a metric that's doing better than the RMS or something like that.
Thanks, Lily.
Okay, so at this point, why don't we shift over, Lily, because we promised folks a hearty discussion about what data challenges we should be thinking about in the future and how we can start planning for those. And so I think you had a spreadsheet that you were going to share and kind of facilitate this conversation, and I'm going to frantically take notes in the background.
Yeah, sounds good. I hope I didn't put anyone to sleep because I am expecting everyone to join in the discussion now. And so I kind of drew up this spreadsheet where I kind of organized my thoughts, though I'm also willing to have a discussion about different ways to organize it. And so the different elements are, over here we have something the critical things, so things that we really should have done before we pursue this question any further. And something that comes to mind is something that came up, I think, at the GPRV meeting at Oxford a few months back, is we should have a good definition for the exact question that we want answered. So right now, I feel like a lot of people maybe are operating under this impression that we want the scatter reduced, but now we know that the RMS isn't that great, or other people are working on removing any sort of variability from the spectra. And so we should be thinking about exactly what we want answered, and then it will help us figure out how we want to reach that goal. And so for the roadmap aspect of it, I have it sorted into things that maybe are next steps that we should be considering doing directly following the results of this first ESSP pass. Things that maybe we want to do 1 to 3 years from now, give us time to collect new data, give us time to develop new methods or things like that. And also longer term goals. So things that we can see in the future being really helpful, but it's not either pressing or something that you see being immediately possible. And the different categories that I can see us discussing are data. So what sort of data do we need? What sort of test sets do we have? Is it simulation? Is it real data? What sort of instrument do we want to take them on, et cetera? There could be this idea of what exactly are we comparing? So what should we be providing? What should we be asking people for? And what should be the return be? And then the last one is metrics. So how are we gauging how these methods are performed? Is it something that we want to ramp up throughout the years, or for different data challenges? Is it something we want to implement right away? Things like that. And so I have here some ideas. For example, this year we're working on the solar data comparison already. And the thing that I hear time and time again is the importance of having these injected Keplerian signals to make sure that we're not getting rid of any planet signals with these different methods. And there's also been this idea of doing a similar ESSP type comparison, but a different pipeline. So different ways that RVs are extracted, different ways of caloric modeling and things like that. And things that I can see for the future is continuing to gather data, these ESSP stars, which EXPRES has been doing all along, but also this discussion of introducing standard stars across different instruments. And so if there was a sort of shared list of standard stars, could we recreate the solar data comparison among different instruments? And is that something we should be working towards? In terms of comparison, right now we are just comparing the RVs. So is there something we want to compare that's more intermediate? So for all the PCA driven ones, we want to compare the principal components or their different amplitudes as a time series to see if they're picking up on the same thing. Do we want to compare the different indicators for the metric driven methods and see if they agree with each other? And then goes into the suggestions of like mixing the different model methods and also maybe implementing in the running of the challenge some sort of uniform training validation structure for each of the methods to implement. And some different suggestions that I've gotten for the metric to use is, instead of just using RMS, we could instead take everyone's RVs and run a sort of detectability. So what planets would remain hidden with the new cleaned RVs in period mass space, for example. And that would get at this question of what planets would we be able to find if this method got rid of all the stellar signals. We could take a more Bayesian approach to it and use a this method to present some sort of likelihood function and calculate the posterior distribution from that and see how much it matches the posterior distribution we use to inject planets. And something else we should keep in mind is that the metrics should capture the noise properties of the data being used. And so here are some of the ideas that I've gotten from peddling this talk all over the world. But I'd love to hear from other people if they see any other critical things that we'd like, whether they have opinions on where these should go in the timeline or other things to add to these boxes or any other columns to add. So as I wait for people to talk, I'm just going to correct some few typos that I found while talking about this. But yeah, if anyone wants to raise their hands and chime in.
Okay, I'll take the host's prerogative while other folks are formulating their thoughts and follow up on your 1 to 3 year plan of data across standard stars for different instruments, and mention that this idea came up briefly in the RCN Slack, and I think it's an interesting one to follow up on. So we were talking about whether this could be like a set of coordinated observing proposals, because I think maybe we all know that it is often challenging to convince a TAC that it's worth spending nights of precious telescope time observing stars that you don't think are going to be doing much. If you're not, confirming a new planet, that's a harder science sell. but there was an idea that maybe if we pitched this is a global coordinated effort and we have proposals going into this whole network of facilities for, across 1 year of observing or across a few semesters, that might increase the perceived science value of what would come out of this and make it a better selling point. And so I think Jinglin just mentioned this idea of like having a subgroup or a task force or something. I'm wondering if this is, maybe another topic that could be a subset of the folks in the RCN focusing on and making sure we have representatives for, each of the facilities that might be interested in participating to craft their specific proposals that they all go in together.
Yeah. So maybe Jen or John, can you maybe briefly comment before we start a larger discussion of maybe the role you see the RCN playing in this roadmap?
Yeah, I think this is something where we do not want to step on what you are already doing with the ESSP. And so, no part of me wants to take on objectives that you want the ESSP to be handling. I think I envision the RCN as a support role. And so if there are things that are, outside the bounds of what your existing group wants to tackle, that we would happily step up and try and provide organizational support, man hours on the logistics and the coordination and setting up meetings, helping to put together agendas and notes and things like that.
Awesome. Does anybody have any thoughts? Oh, sorry, David, go ahead.
So this isn't really, I don't think really answering the question that you just asked about what you presented here, but I have a general question which might help with the discussion. So all of this that you're showing is very much oriented from observing and modeling real stars, going out and getting observations of stars. And the problem with that is that you don't actually know what each individual piece of the star is doing. So how do we move forward? Like, this is just an example, but like take some of like Rachel Rottnocker's work, all right, and then build a star model and forward model this, so then you can then control each piece, right, and have a better idea of understanding, okay, this is how the line profiles are changing, or this is how the pulsations are adding, or this is how the rotation is dealing with it. So I'm suggesting this without any real expectation of, or sorry, any real understanding of how difficult the thing I'm asking really is. But I thought that might be a good discussion point to try to come at this from a different direction, since other than the traditional direction, which is what we've been doing for the last 30 years, which is here's a bunch of data and try to understand it from the outside in. What about trying to understand it from the inside out? Anyway, I'd like to hear your thoughts as well as everybody else's thoughts, including Rachel, since I invoked her name without her permission.
That's a great point, David. Thanks for saying that. You caught me. I'm an observer. And so I haven't included simulated data on this, but it's a great point. I see Rachel has her hand up. Rachel, did you want to comment on that? And maybe do you think you could figure out which of these rows this idea of using simulated data based off the work that you were doing could go in?
Sure. So I'm more than happy to share the data sets once we've published them. I already have talked about that with Lily about putting that on the ESSP sort of horizon. So I'm more than happy to share the images that we end up with from the interferometry. I've been working with Sam Cabot, who's a grad student here at Yale, and he takes images that I create. So far, we've only done it with light curve inversion, and reconstructs or simulates what the radial velocities or what the spectra would look like from the star by breaking the star down into the sort of pixels that I give him. So I think this is definitely a doable thing, and we can definitely start considering adding in more complicated models on top of it. Some other features like information about the convection, things that, you know, we can't actually resolve with the interferometry. So I'm more than happy to help provide these things, provide the images and share them with the community. As for the time scale, hopefully one of them will be available this year, but 1 to 3 years definitely.
And I'll note that Paul Robertson just mentioned in the chat, I suspect David's idea will work well for sun-like stars, but maybe not example for fully convective stars.
All of the stars that I'm working to get data on right now are sun-like stars, loosely defined, but they're not fully convective, if that's of any help.
Sure, and that's actually a really important point. I think where I was going with this idea was that I think it's worthwhile to think through, you know, how could we do this? How could we forward all the stars? What data would we need? Like from Rachel's program, what other people would we need to get involved to help us understand the effects of the interiors, the effects of the different sizes of the convection zones, right? You know, all the way through the sequence. And I agree that we would probably want to start with, you know, something like G stars, where we probably have our best understanding because of the sun, that kind of idea. So I guess what I'm suggesting with this forward modeling is that if it's going to be useful at all, we have to really think through, you know, what it is that we want to do, how do we do it. I was throwing out an idea to help us approach this from a different direction without any real acknowledgement of the difficulties in doing all of it.
We respect aspirational ideas here. Nothing wrong with that.
I'd love to get a sense of from people about whether people are more excited on getting new data to test their methods on, doing comparisons to better understand what their current methods are doing, or trying to come up with like new ideas for methods. Is there like a preference for one over the other? Nathan?
Yeah, can you hear me?
Yeah.
Okay. So we discussed it by email, but I think it would be interesting to do an injection recovery test, because you can do it in a way where the question is very precise and you can isolate exactly what you're testing. And testing the different qualities of likelihoods is combining both the idea that regardless of our model, in the end, we want to confidently detect planets. And on the other hand, to do this, your likelihood needs to grasp as much as possible as the stellar variability. And so, as I told you in my email, I think if we generate planets with certain priors and give those priors to the teams who analyze the data, then we can really isolate the effect of the likelihood on the planet detection. So I would be interested in a challenge like that.
Sounds great. Okay, so that sounds like a metric thing. So I try to capture your idea here, but perhaps I did it in too shorthand. But like metrics that more specifically hold the question at hand. Any other thoughts on whether we should be prioritizing data, metrics, or a comparison currently?
I think your figure showing that, you know, just how far short the RMS falls is something that makes me think the metrics are a key focal point moving forward. What the better metric is, I don't know, and whether that metric, what the ambiguity of that metric is it tied to what David was saying about we don't know physically what the exact right answer is, and so it's obfuscated a bit. Seems like a fun thing to try and disentangle, or a challenging thing to try and disentangle. I'd be curious if folks, oh, sorry, Jesse, I see your hand up. Why don't you go ahead?
Oh, thank you. This is just another thing to throw out there. Someone had asked about it during your talk, Lily, but maybe something if working with simulated data or injecting planets looking for or assessing the optimal sampling, and this might be a method level assessment where, you know, if you're looking at Gaussian process methods, what's the optimal sampling for uncovering planetary signals versus the activity? But that could also then maybe help with the observing proposals, because if you know or have a sense of we need this number of days in you know this amount of time in order to uncover a signal, maybe that would help strengthen a proposal potentially.
Nice. Yeah, that's a great idea. So that's something else that we could get out of this sort of comparison, other than just different method performance and what signals that people are getting at.
Yep.
So on that note of what exactly we're looking at, I did want to come back to this idea of this critical thing of defining the exact question that we want answered. I think a lot of the work that we do and a lot of the things that the community gathers around will depend on this question. I don't know if it's something that, I think it's something important that the entire community agrees on. Maybe it's more in the RCN's framework, but since people are gathered here and thinking about these issues, I wondered if anyone had any thoughts about the sort of things this question should reflect, or the sort of things they're thinking about that they would love, that they would need for this question to reflect, things like that.
I mean, as a very rough first pass, is this something like what combination of observational data and modeling approaches are necessary to reveal, you know, Earth-like signals? Is that what we're thinking about here, or do you have something else in mind?
Yeah, so it would be focused on like combinations of methods, models, for the purpose of revealing Earths.
Mm-hmm.
I might add data type.
Yeah.
Data quality. Other thoughts?
David Ciardi just mentioned in the chat, from an observational point of view, what combination of spectra / RVs across a range of wavelengths, so optical to near IR? Yeah, in imagining the like block diagram of this, I feel like block 1 is, you know, what data are you taking and how are you taking it? And then how is that data being fed through first the RV reduction pipeline, and then second, the activity sensitivity / modeling box.
So like 1, what data are you taking? 2, how are you making that data useful? 3, what are you doing with that data?
It's not, yeah, basically.
Yeah.
And I think there's, you know, a lot of things that go into each of those boxes that we could have endless conversations about, but that's maybe the big 3 steps of this process.
Nice. Okay. So taking the data, extracting the data, and then working with the data. So that kind of reflects in sort of like the data quality and then the methods and models. Okay. Andreas?
Yeah, I wish I had a comment that makes it easier to focus and, you know, sharpen the view on the problem at hand. But it's more the opposite what I want to suggest, which is like, it strikes me that you brought together this real wealth of different methods to actually, analyze the data. But there's still the underlying problem of, so far we've only looked at a small number of stars and data taken with just one instrument. And I think it would be really helpful to make the database we have broader, not necessarily the techniques we are applying. So having more, the data from different instruments for the same stars, that goes back to the question of defining a sample of standard stars, with being standard just meaning that you're basically looking at the same stars and committing to those in a certain sense. But also having different instruments looking at these stars, right? I think one of the big benefits of the Sun as a Star project is it helps us disentangle stellar and instrumental effects without us necessarily understanding what each of them are. But simply to give us an idea how realistic our expectations actually are in terms of, like, as you said before, okay, we have other stars that show an RMS of XYZ, and so we should be able to get down to those levels for the other stars as well. But is that really true, right? And one of these questions is how much of instrumental effects is still hidden in those data sets. And so I think it would be very helpful to broaden our database in which we apply those methods. And in the same vein, it's also important to broaden our range of techniques we apply to the raw data to extract the RVs, right? Not only in question of, okay, what data extraction pipeline we are using, is it a CCF based one or is it a template based one, but really also going into the nitty gritty of how are we actually maintaining instrument drift correction and stuff like that, and how much influence does that have on the individual data sets. When I look at Neuron X data, for example, I'm always concerned about that we get to these like sub-meter per second precision data by combining a wide wavelength range, for example, right, where we average over a lot of systematics. But then when we apply our data analysis techniques and we suddenly say, oh, the blue, and I'm just being very general here, the blue region is more active, so we want to go actually to just weather wavelength. Or just by looking how in particular spectral types radio velocity information is distributed. And then it's really scary to see at some points that you only get most of your radio velocity information from very small sections of the spectrum, right? And then suddenly your impact of instrument systematics becomes stronger and stronger. And so at some point I would expect that different instruments, with different wavelength regions and different resolving powers will give very different answers, right? And somehow we have to figure out how the interplay of that is with the data analysis techniques.
Yeah, no, I really appreciate that comment. I think it ties in nicely with Jesse's comment as well, where I feel like it's the way that I give the talk and the way that I wrote the paper, it's very one track of like, you get the data and we figure out what you can do about the stellar signals. But with these different methods and these different tests, we can vary the stars, the instruments, and the methods. And by doing so, each one informs the other. So we can use the methods to learn about the stars, to learn about the different instruments. And we can use the sampling to learn about different observing cadences, different resolutions, all these things. So they're definitely all connected to some level. It's more of a web than a table. But thanks, that was really helpful. I got a lot of good thoughts and a lot of different ways to think about things. I'll stop sharing now because I think we're past the hour, and I think Jen, you have something you wanted to add, but thank you everyone for your time and your contributions.
Yeah, and thank you, Lily, so much for an excellent talk and an excellent prompting of this conversation after the fact. That was great. The one thing I just wanted to mention to folks is, again, thank you for calling in to our kickoff meeting. This was wonderful. Just to let you know, next month on June 23rd, we'll have our next colloquium, this time featuring Susanna Grain, who'll be talking to us a little bit more in detail about GPs and their uses in trying to search for small planets. So we'll be diving into one particular type of activity mitigation and the work that she and her group are doing with that. Because Suzanne is calling in from the UK, we're moving this to be a little bit earlier, so that talk will be at 9 a.m. You will get a variety of reminders about this over the coming weeks, so it'll show up as calendar invites and such in your inboxes. And as always, we are looking for suggestions for future events. And so if you have suggestions for colloquium speakers, please use the first link there. The self-nominations, more than welcome. It's anonymous, so no one's going to know that you nominated yourself. But if you think you have useful things to say that would benefit the RCN hearing about, please put them in. And then we're also looking for ideas for new workshops, town halls, science seminars, things like that as well. So this could be requests for tutorials you'd like to see, topical things like the stellar activity seminar we did last month, but maybe focused on instrumentation or observing techniques or things like that. So ideas for all of that are welcome as well. I'll send those links around again in a future email when I send the recording of Lily's talk. So be thinking about that. And yeah, aside from that, thank you for calling in. Thank you for a great conversation. Thank you to Lily for giving our talk and for leading the conversation. I think this was a great kickoff to this series.